All right, so I got a conundrum. So you guys have heard of the Cybertruck, right? Tesla Cybertruck. Well, I can get the Founder Series, one of 1,000.
Do it.
I was in the top 1,000 for pre-orders. Do I get it?
Yeah.
I just got a $100,000 car this last summer.
Fuck. Got a ball.
I have a pontoon rental business that I own that somebody else runs for me, but I mean, could it just be a land pontoon that we rent? Would people rent a Cybertruck?
Yes.
You think? Because it'd be funny. And do I logo it out with awesome fat stuff all over it, or do you just leave it, or do you just do something crazy with it, like ink it up with like get some kind of tattoo artist out who like? So I'm thinking about it. Even if I don't fully believe in all electric cars, I mean, I had a Tesla for 2.5 years, and I mean, I loved it, but there is a need for gas sometimes. I mean, is there an investment value in having a 1 in 1,000 car from Tesla? You think? Because usually cars drops down.
Get a bunch of Ninja Turtle stuff.
Just put Ninja Turtles all over the Cybertruck. I think that would hurt it. You have to keep it cybery. You can't just throw Shredder on the front of it and hope for the best. So I don't know. I'm debating. I'll probably decide by the end of the day. Let's see. All right. Let me make sure I'm recording. Yep. All right, everybody see the screen okay? All right. So last time we were talking about threads. Well, we talked about really we were talking about this idea of programs that block. And so let me give you you know, instead of just saying that word, let's see an example of that. Oh, just as a reminder, I think I told you already, but we'll be on Zoom on Friday for class, and hopefully anesthesia will have worn off by then, or we'll have a really good class.
Oh, I think I forgot.
So
I
Friday.
didn't know we were on Zoom Wednesday. Sorry.
Oh, no, you're fine. There's other people on Zoom with you. So I always have Zoom open, but on class, on Friday, I'll only be on Zoom. So just heads up for that. All right, so let's look at some examples. So we're going to start off with our generic Hello World program like usual. You know, like I said last semester, I like to get something set up. That way you can just hit run and you know it's working. I'm on online GDB right now. We'll only be messing with this for a couple of weeks before we jump over to Unity. But so if you have a different Java IDE you want to use, that's fine. But this is as good as any. So I have it saying hello world. All right. So now I'm going to go ahead and let's write a program that just does something to the screen. So for it die is equal to 0, high is less than, is that 1,000,000 maybe? I plus plus, just something that goes on for a while. All right, so that's 100,000, that's 1,000,000. Okay, that'll run for a while. Okay. All right, so there's a program that's running not for infinity, but it'll keep cooking for a while because it's running through 1 billion times and it's printing out each time through. I know I had mentioned this last time, but just to give you a connection to what I meant, well, last semester rather, but just to give you a connection to something I mentioned last class. I mentioned that how like processors are scheduled for the operating system, and these individual processes, they have to get in line to use the CPU. And it's expensive when they get onto the CPU and when they leave the CPU. That's something called a context switch. Well, I think last class, we made this assumption. I think I just said, keep it in human time. Let's say each process gets 1 second on the CPU. It gets far less than that. But what's happening here is this process gets onto the CPU, does a little tiny math instruction, and then immediately has to do input output. And input output is something that's handled externally to the CPU. So that means it gets a context switch, means it's either unpacking its bags as it's getting onto the CPU, or it's packing its bags as it's leaving the CPU. So this is a situation where it comes onto the CPU and unpacks its bags, putting stuff into the hardware registers, things you'll learn about in 325. Does like 1 or 2 things. Tiny fraction of the amount of things it would be allowed to do if given its full run on the CPU. Then it has to repack its bags and get out of Dodge. Extremely inefficient. That's why we're able to see this count like this, where there's so many pauses. But what we're actually kind of seeing is how often this process also gets CPU time back. Okay, so I mentioned last time that the computers are really fast. And even when we had single core processors, their job was to convince us that everything, the whole computer's horsepower was getting put onto this guy. All right. So I'll stop that at that. We see that we have something running for a while, but what I'm going to do is I'm going to go ahead and create a scanner. Just to read something in, and I'll do something like system.out.print, enter a number, whatever. And then we'll say int num is equal to integer.parse int input dot next. It's next line. And then we'll have our loop go through num number of times. All right, so I'll create a scanner. I think this might be inside of java.util. It'll yell at me in a second if it is. Yep, it's in java.util. All right, so I'll build my scanner around system.in, which is the keyboard. We'll prompt the user, enter a number, whatever. Then we're going to say input.next line. That's how the scanner reads a string in from the user. We could have read in the next number as well, and not that I wouldn't have had to parse it, but this allowed me to remind you of how to get a integer out of a string by throwing this integer.parseInt in there. All right, so I'm going to read in some number as a string, convert that string to an integer, store it inside of a variable called num, and then I'll have my for loop run that many times. So it's asking me for a number, I'll type in 10, and it ran 10 times, 0 through 9. All right, make sense what the code's doing right now? This code right here does not run until after the user hits enter. Line 17 is said to, oh, that needs to be inside of a comment, is said to block. All right, so here on line 17, because we're waiting for the user to type something in and press enter, we can't progress in our program past line 17 until the user presses enter. So if I hit run and I don't touch the keyboard, it's sitting here at line 17 waiting for me to type something in and press enter. So I don't get to that loop. I'm blocking the rest of my program from running. Now, in this particular case, that's a good thing, right? Because that loop is reliant on the number I type in. It's waiting to run some number of times based on the number I enter. So it makes sense to block in this case. But if for some random reason I wanted it to just print out all the numbers between 1 and 1 billion to the screen while I'm prompting the user for something just because, and I didn't want the waiting for the user to block that from happening, we might look at solutions to have more than one thing happen in our program at once. Make some sense? All right. Now, last time we talked about the old school way of doing this would be to spawn off child processes using the fork system call. That creates a heavyweight process. So, I mean, when I opened up Chrome becomes a heavyweight process, a top level process in the operating system, which has, CPU time associated with it, which has a memory block associated with it, which gets its own virtual space associated with it. Lots and lots of stuff are hanging off processes, all right, making them use up resources. So we don't want to just create processes willy-nilly, especially if I mentioned last time, one of the things that early hackers would do is they would write a program that just kept creating child processes over and over and over again until the operating system ran out of unique process IDs. And that's only 65,536 times through the loop. That's not that long of a loop. So you basically brought a server to its knees, and the server administrators couldn't even get into to close it down because they couldn't launch the terminal to kill the processes, because launching the terminal would create another process ID, which they were out of. So in the earlier days of like Unix system administration, what you could do is you could go to and physically access the computer, and you can use one of the serial ports, which already had a listening console on it, to kill off processes that way. So you had a fighting chance of maybe regaining control of the operating system without hitting restart. And you got to consider that for our computers at home, restarting them is likely not a big deal, right? I mean, you just saved your document with Microsoft Word or whatever. But on a server that might have hundreds or thousands of users, and they might be running an experiment or something like that that's been running for 6 days and has 20 minutes left on it or something like that, rebooting the machine has cost, right? Makes sense? So if an administrator can avoid rebooting the machine, that's beneficial. Oh, and by the way, I'm not sick. I just have really bad allergies. And when I came from the Caribbean to this climate, my sinuses want to die. is what it comes down to. But I'm not ill, I just sound ill. I always have the issues when we start the summer or finish the summer, as we have those some cold days, some warm days. And this is like that on steroids. Because down in the Caribbean, it's like, I don't know, every day it's probably 87 degrees and 100% humidity. Then I come back here and it's 25 degrees and some negative number percent humidity. It's just killing me. All right. So we would call this blocking code. As we see, it's blocking us. Make sense? And sometimes this is a problem. All right. So when it's a problem, we want to find workarounds. And because there are downsides to creating full size heavyweight processes, we look at a more modern approach to this where we create multiple threads. Now, that isn't to say that in every single circumstance, a thread is superior to a process. Sometimes it does make sense to have full heavyweight processes, have your program split into two heavyweight processes if those two things are going to be doing something for like a while. And they have like legitimate, you have a big time program that's doing something and it needs to do two separate things at once. And this isn't just like a quick, just do something for a few seconds and be done. This is something where it's going to run for the duration of this program. And it would really be beneficial if it got its own operating system resources and things like that. You also have to consider, depending on what that program's doing, does it need direct access to the operating system? If so, it probably needs to be a real deal process, as opposed to, does it only need resources that it can indirectly access through its parent? In that case, it can be a thread. A fair assessment would be that 99% of the time, threads are more than enough. They accomplish the task of us having a couple of things happening at the same time, as long as those things aren't reliant on each other. Okay. But just know that it's not that processes are antiquated. It's still a thing. We just have a new tool that allows us to do something that really only impacts us. We can't take over you're not going to accidentally write a program that spawns off too many threads and kills your operating system. Well, especially Java. Java has some brick walls put around your running program in a virtual machine, and it's only going to let you probably create, I'm guessing it's like 128 threads or something like that before it starts screaming at you, or until you have to start giving it command line options when you run it. You can give the Java virtual machine some directives and say, give me access to more memory, give me access to more threads, yada, yada, yada. But the default keeps you inside of some whatever. Okay. So let's look at our threads. We looked at the thread documentation last time, and we saw that thread in Java implements an interface called runnable. That's this guy right here. And runnable, you can almost think of this like as being a member of a club. An interface is not an implementation. It's a requirement to implement something. All right. So the thread class has said, we want to be a member of the runnable club. So we're going to implement runnable. That's the keyword. So like with inheritance, we use extends. The version of that to take into consideration the interface is the keyword implements. It's not something you're going to run into all that often, is the reality of things. But you do see it in the documentation pretty often. All right, if we click on runnable, we're going to say runnable says, in order to be in our club, you have to have a method called run. This guy. You have to have a non-static method called run. All right. So it just so happens thread has decided he wants to be a runnable, so he's going to implement runnable, and he has a whole bunch of methods, but one of those methods down here is called run. Right here. So he indeed met the requirements to join the runnable club as he applied by saying implement runnable. So he said, I want to join this club, and then he fulfilled requirements by writing this method. It does not say anything about what that method does. It just says it has to be called run. It takes no parameters, and it returns nothing. What you do inside of there is completely up to you. You can just, print 1 to a billion if you want to. All right. But I mentioned last time in threads are something that's at the operating system level. All right. This is, so there's a level of magic, if you will, that has to occur in order for our Java program to actually create threads behind the scenes. All right. And that's not something that the Java virtual machine gives us as programmers direct access to, but we have indirect access to it through the magical method called start. All right. So the makers of the Java programming language, they wrote the thread class, and they put the magic inside of the start function, the start method, that will execute whatever you put in your run method. It will execute that inside of whatever magic needs to happen to spawn a thread. All right, makes some sense? All right, so that's kind of behind the scenes stuff we're not going to see, but at the end of the day, it's the operating system calls that are going to get called to most of our modern operating systems use a library called pthreads. Mac does. Microsoft's library is equivalent. It's something else because they have their own system calls, but it's the same thing. But multi-threading is something built into the operating system, and the Java program's deciding to participate in that. All right. So by default, if we create a thread, go back into my code here. So I can say, okay, well, I'm going to create a thread T is equal to a new thread. And then I can say T.start. And that thread will have started. It's done. It's going. It's going to immediately end, because what does the start function do? The start function tells the operating system, go create me a thread. Done. Now what should I do? Execute whatever code's inside of run. That's what threads do. The problem here is we're working with a default thread, which means that the run method actually has nothing in it, which means it starts at the first line of run, sees you want to do nothing, hits the end of run, poof, done, thread's gone. Perfectly legal code. It's not going to throw us an error, but it's also not going to actually do anything. All right. Now, I assume we probably like it to do something. It's kind of the goal here. So what we're going to do is we're going to say, you know what? I want to make something that is a thread, but I want to differentiate myself from the default behavior of threads. The default behavior that is, I know how to do the magic to become a thread, but I don't actually do anything inside my run method. So we're going to create our own file here. I'm going to call this guy a worker bee. We'll call it a worker bee thread, just so we keep that that name in there. I kind of like to think of threads as worker bees. They're doing something off on the side that is happening without being blocked by the other logic of our program. But typically we want to think of our worker bees as doing things that don't necessarily rely on input from other parts of our program or rely on minimum input, because we do have the ability to get threads to talk to each other. If two threads are working on something that ultimately they have to come back together with and say, okay, well, I got my answer. Do you have your answer? Yeah. Now we can finally give a final answer. You know, that's something you could do with threads. So they would kind of need to coordinate a little bit. That exists. But for the most part, the first reason to use a thread is to bypass blocking code. All right. So I'm going to call this guy worker bee thread. All right. This is going to be public. Well, actually, it doesn't have to be public. So we're going to say class worker bee thread. And we're going to say this guy extends thread. So we want him to be everything that the generic thread is, but a little bit more. Okay. We're going to have him uniquely. So we're going to say public void run. So we're going to say we will write our own version of run so that the start method calls this version. And what I'm going to do here is I'm just going to come over here and grab my little 1 to a billion for loop. That's what we're going to have run do for no good reason other than say I want to do something. All right. So now I'll enter in my number and we'll just do a system.out.println, whatever they enter in. And then the program will end. All right. So instead of this being a thread, it's going to be a worker bee thread. And we'll tell that guy to start. So right off the bat, we create a sidekick. We bring into existence, we instantiate a worker bee thread, and we say, go to work by telling it to start. And what does a worker bee thread do when it goes to work? It does whatever run says to do. So he's going to start going through a billion times, printing out 0, 1, 2, 3, 4, 5, blah, 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 blah. Now he's printing it out to the screen. So we're going to see those numbers out on the screen. We're only going to see that prompt. You're going to have to really look for it as it blows by. Here we can try to give it a like a comet trail or something. Maybe we'll see it, because it's going to happen real quick, right? As soon as I instantiate my thread and I tell it to go, that thread's off to the races. Our program is just going to keep cooking here inside the main thread. So all processes have a main thread of execution. Think of it as the parent thread. And all these other ones are child threads. All right, so right after our thread gets to work doing its thing, you're going to see our program here start doing, its thing. All right, probably didn't even see the asterisk there, but it is waiting for me to put in some input. So I typed in some input. It's whatever, that thread's still off to the races. Let me try to give you a example. All right, well, for right now, just trust me that I was able to enter stuff in. All right, while that thread was out there doing some crazy stuff. If we want to make our thread a little bit here, why don't we just make it go through 10 lines? All right, so our thread is done. It's still waiting for me to enter a number. Put in my 10, whatever. It went and did its thing. But what we want to see here is, how do these threads compete with themselves? All right, so what I'm going to do is I'm going to create a couple of threads and have them printing out all these numbers at once, but I'm going to give each thread a name. All right, at this point, we've differentiated our worker bees from threads only by the run method, having a run method that does something. But this is our own class. Classes are made up of what three things? What are the three members of a class? One of them are methods. Go ahead. Constructors and fields.
Field.
All right. So fields are our variables. So maybe we create a private field that's a string. Maybe this is the name of this thread. All right. Then we need to have a constructor. So constructor always has the same name as the class name. And we'll have this guy take the name in. And we'll set that dude's name. So now when we create a worker bee, we'll pass in his name. It'll store that name inside the field called name. And now when I print out a number, what I'm going to do is I'm going to say this dot name concatenated with a space. We'll put a little arrow after that, concatenated with whatever the next number is. That way, whenever we see something printed on the screen, we know who's printing it. And we're going to create a couple of different threads and give them some names. Make some sense? All right. So when we create a thread, we're going to have to give it when we create a worker bee thread, we're going to have to give it a name. We'll give them distinctive names. Then when we tell that thread to start, it's going to go through a billion times. That way it'll be going for a while. And it'll say my name, whatever that thread's name is, followed by an arrow, followed by its number. So let's create a couple of worker bee threads. Am I spelling these right? That's Michelangelo. That can't be right. How do you spell Michelangelo? Is that right? No, we're going to leave it. Maybe that. Here, we'll just put those guys in there. Which one was my original?
The one you have.
That's right. All right, we'll just go with it. And this is Leonardo. I'll have to change the variable names. Donatello. Raphael. We have our 4 threads. We'll tell each of our threads to start. And I'll go ahead and still have my input for right now. You'll see why in a little bit. All right, so 4 worker bees, all of them get started. Each worker bee has a unique name. What does a worker bee do when it starts? It calls its run method. Its run method goes through a billion times, prints out whatever this thread's name is, followed by a number. So now we'll get to experience how these threads are being scheduled. And we see the names changing in there. Okay, so a thread is getting some CPU time, and then it's handing off its CPU time to another one, is handing off its CPU time to another one, so on and so forth. And all these threads are sharing the CPU time with the parent. All right, so we're experiencing it all through a single window because they're all printing to the screen, system.out. They're all printing to system.out. Okay, but these 4 threads are working independently in the background. Now, threads don't have to print something to the screen. They could be off doing their own little thing, right? Nothing prevents them from doing that. All right, so remind me, did we do merge sort last semester? Oh man, if we did, you would know. So we're gonna do it right now. Man, your week just got ruined. And the reason I'm choosing merge sort is a divide and conquer algorithm where you can split things up. All right. First of all, any questions about threads? Good with that? All right, so let's look at the algorithm for merge sort. So we're going to be sorting some numbers. Now we're going to put a pause on threads for a second, and we're going to bring them back into the story when we upgrade our merge sort. All right, so you see value in merge sort. So first of all, I want to talk about something called recursion. I'm sure I mentioned it last semester. Recursion is when a function calls itself from within itself. All right, so this is when a function calls itself from within itself. Usually the first example of recursion we look at is factorial. So 4 factorial is equal to 4 times 3 times 2 times 1, right? Which is 24. Isn't it true that 4 factorial is equal to 4 times 3 factorial? And 3 factorial is equal to 3 times 2 factorial? And 2 factorial is equal to 2 times 1 factorial? And 1 factorial is equal to 1? Okay, so instead of writing factorial iteratively like this, let's go with that, which we're going to go ahead and write. Stop our worker bees for the moment. Here, let me. Whatever. Nah, just write this down here. So we're going to have, I'm going to make it static since we're calling it from within a static context inside of public static void main. So I'm going to be calling it here from main. This guy is static, so I'm going to have my function be static that I'm writing. We're just going to have this guy be void. We'll have him just display. No, we'll have him returning it. And we're going to call this iterative factorial. And he'll take a number in as a parameter. All right. So if we do this iteratively and we use as an example, num is 4, just as an example, we want to do 4 times 3 times 2 times 1. So we want to go from the starting point all the way down to 1. Technically, you don't need to include 1 since anything times 1 is itself, but for the sake of completeness, we will. So I'm going to go ahead and say int product is equal to 1. We're going to start a loop for int I is equal to num. I is greater than or equal to 1. I minus minus. And we'll say product is equal to whatever product currently is equal to times the current value of I. Technically, you could have started product off at num and then started I off at num minus 1 and counted down from there, but this gets the job done. All right. So I'll start my product off at 1. That way, the first time through this loop, if num was 4, we'll say product becomes 1 times 4, which is 4. The next time through, product becomes whatever it used to be, which is 4 times 3, which is 12. Next time through, product becomes whatever it currently is, which was 12 times 2, which is 24. So on and so forth. Okay. And we'll go ahead and test this guy. Passing a 4, and we'll get our 24 out of there. Ninja. Iterative. Oh, actually, I like calling it with the thing anyways, but that's not the error. Oh, I never returned. So after I calculate my product, I need to return my product. So there's my 24. And if I pass it in a 5 instead, I should get 120. So on and so forth. All right, so that is an iterative solution to factorial. Now, we can write a recursive solution to factorial. So we can say static int recursive factorial and have this guy taken an int num as a parameter. And we can do the same thing we said from the slides here. We said 4 factorial is actually equal to 4 times 3 factorial. 3 factorial is actually equal to 3 times 2 factorial. 2 factorial is actually equal to 2 times 1 factorial. And 1 factorial is 1. So if the current value of num is 1, boil down to 1. Else, boil down to the current value times the factorial of the current value minus 1. So if num is equivalent to 1, we'll return 1. Else, we'll return num times recursive factorial of num minus 1. So that also solves the factorial problem, but it solves it in a recursive manner. Now, typically, recursive solutions to problems are shorter in total length. This particular one, since I have it spread out with the curly braces and everything that aren't actually required, it looks roughly the same size, but typically they do end up being more concise. Now, does that mean recursive is better? Remember last semester I mentioned that nobody's impressed if you have shorter code, right? Shorter code that doesn't work is way, way, way worse than longer code that does. All right. So first of all, the length of your lines of code, unimportant, especially if you should be using comments and variable names with good names, yada, 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 all that stuff. So when do you use recursion? Some problems inherently lend themselves to recursive solutions. The reason we use factorial initially is that it's a pretty clean example of a recursive pattern, even though we can easily do it iteratively, right? It's not a major ordeal. But there are some problems that are significantly easier to solve recursively than they are iteratively. Now, having said that, the reality is anything you can solve, let's put this in a slide. First of all, anything you can do recursively, you can do using a loop and a stack. Stack data structures, these are things you're going to learn about next semester in CSC250 for those of you who are either software engineering majors or AI and robotics majors. And I used to teach that class. I think Blade teaches it next semester. Oh, we got the spelling. All right. So first of all, we want to say that recursion can be done iteratively with a stack. Now that actually gives us some information about what's happening behind the scenes. The way programming languages are built, at some point, somebody had to implement the mechanism for recursion. And the way the mechanism for recursion works is by using a stack behind the scenes. A stack is effectively, think of it like a stack of magazines or a stack of books. The last thing you put on the stack is the first thing that comes off the stack. We push onto the stack, we pop off the top of the stack. All right, that's what a stack is. Recursion works that way as well. We go back a couple slides here. And we say, what is 4 factorial? It's 4 times 3 factorial. I can't finish this math until I get an answer back from that guy. So I have to put that on hold. So I take the current run of that factorial function and I put it on the stack for safekeeping because I'm going to come back to that later while I execute another call to factorial. And this call to factorial also can't complete until I have the answer to that. So I put him on top of the stack while we wait for the answer to this. Go to the next one. This guy can't complete until I have an answer of that. So we put him on top of the stack. So now we have 3 things stacked up, right? 3 separate calls to our function that we're have to remember all the details of those calls. What's num equal to in this call? What's num equal to in this call? What's num equal to in this call? All right, they're all put on hold. Finally, I get to this run where it does not make another factorial call. Instead, it just ends by saying, oh, the answer is 1, which then gave us the answer here so we can pop the top of the stack and finish doing this math, which then gives us the option here, or the answer here, where we can pop the top of the stack and be able to finish this math, which lets us pop the top of the stack and finish this math, which then lets us give the final answer. All right. So having said all of that, what might you say is a downside of recursion? We all saw me pushing a bunch of stuff on the stack, remembering this thing, and then remembering this thing, and then remembering this thing. Might we say we have to remember a lot of things? All right, so memory. Recursion is memory inefficient. We have to use a lot of memory because we're having to pause a bunch of stuff while we're waiting for the end of the recursion. Things get real fun when you have infinite recursion. Because eventually Java screams at you, say stack overflow error. You kept putting stuff on top of the stack until you ran out of stack space, which is good because I mentioned a little bit ago that one of the things Java does, most modern languages do this, is they put limitations because your program's running in kind of a virtual state. And it puts limitations on stack space, something else called heap space, number of threads, this kind of stuff. So I don't know what the stack space default is for Java. Maybe it's 1,024 buckets or something like that. But bottom line is, if you try to put too many things on top of the stack, Java will scream at you before your computer runs out of memory. All right. And usually the exception will be Stack Overflow exception. All right. So here's our recursive solution to this guy. So we'll just throw him in there and get the recursive answer to 120. And that is for the factorial of 5. All right, questions about how recursion works? Now, I promise you, recursion is going to be a skill that's going to take some getting used to. And this is why you're going to hate me by next week when you do your merge sort over the weekend. You actually dodged the bullet last semester. It probably was because I was away for that when you did the quantum stuff that we didn't get to merge sort. Oh, well, man, I hate to be in your shoes right now. All right. So you should talk to seniors to say, you know, did you ever do merge sort? They're going to be telling you horror stories about it. But eventually, merge sort actually becomes easy. So I'll give you, since we're only got a couple minutes here before we dive into merge sort too much, let me just throw it in a slide so we know where to start next time. The idea of merge sort is you have a collection of unsorted numbers. And what you do is you say, is this collection trivially sorted? Well, what does it mean for a collection of things to be trivially sorted? It means there's only one thing. If I hold up a single playing card, is that card sorted? Yeah, because there's nothing else to go before or after, right? There's only one thing. So so merge sort operates on this idea of we know things are sorted when there's only one of them. So we say, is this sorted? No. So what we do is we call merge sort in the first half, we call merge sort in the second half. Is this sorted? No. We call merge sort in the first half, we call merge sort in the second half. Is this sorted? No. We call merge sort in the first half until we finally get down to a sorted thing. Then we bounce up a level, we do something, we do the merge step. We do something else, we do the merge step, yada, yada, yada. So what's fun about merge sort and what's going to terrify you is I already said that recursion is a little bit tough to wrap your mind around, even though we used factorial and it's like it made good enough sense, right? Factorial is an easy enough thing, but to start thinking recursively is a challenge. So be prepared for that. But merge sort actually calls itself twice. It calls merge sort in the left half and then on the right half. And this right call never gets called again. You know, this guy doesn't get to proceed until this guy's unraveled. We go down the left side all the way, which has left and rights, left and rights, left and rights. And as soon as he bounces back up, we have the left side of our list sorted, and we're just getting started on the right side. But those two calls to merge sort usually breaks your spirit. That's what I see in students. So I look forward to that. Good news is it's a long weekend, right? So I think we don't have class Monday. So now, but the punchline for all this will be, you'll eventually, those of you who are software engineering majors, will take 470, which is language theory, which is another class that I traditionally teach. But I taught Blaine everything I know about it. So he teaches that class now because I'm teaching a lot in the grad program. But that class, we use a language in there called scheme, which doesn't have loops. Which means you have to solve every problem recursively. No, what ends up happening is when you come out of that class, you almost only can think recursively. And you have to almost retrain yourself to give yourself iterative as an option. And then that really completes you've arrived as a computer scientist at that point. I promise you. Been training programmers for a long time. You're going to hate this assignment, but eventually you'll find it, well, I haven't given it to you yet, but eventually you'll find this very good for your overall education. Well, that's true. Yeah, my parents said the same thing. I just got off a month-long cruise with my parents. I appreciate them way more now than I did when I was a kid.
Same. So for the tic-tac-toe board, I couldn't figure out why you said 5.